Hi, you're welcome to Quiver Analytics, and we'll be practicalizing the inferential statistics, statistical analysis, and we're starting with test of mean differences. So in statistical analysis, or in data science, there are several tests you can do, but the the rampant ones are the test of mean differences where we have mostly is experimental design. Um, I don't want to bore you with technical stuffs, so and to make this video as short as possible. So for test of main differences, we have the t-test and the ANOVA. We're looking at t-test and the ANOVA. The t-test, there are three types of t-test. We have one sample t-test, independent sample t-test, and paired sample t-test. So for one sample t-test, it tests whether the mean of a single sample differs from a known hypothesized value. All right. So, for example, if you want to test, or maybe there's an argument that the teenagers in a street are not more than 18 years old. I mean, someone is saying they are 18 years old. Another person is arguing they are not, on the average, they are not 18 years old. All right, so 18 becomes the hypothesized value. So there will be a hypothesis that they are significantly 18, they are not significantly 18. So the one sample to test only collects a data, collects a measurement, and tests against an hypothesized mean value. Then independent sample to test compares the mean of two independent groups. We want to compare the mean, same measurements but two different groups. So if you want to compare the, say, BMI of boys compared with average BMI of girls, that will be an independent sample t-test. While for paired sample t-test, we are collecting on the same group but at different times, given that something has happened between those times. So it's a before and after analysis. That's the paired sample t-test. So now let's get into it. To bring in data, we are importing pandas, and then we read the nurse cap data. All right. So what this data is about is some group of pediatric nurses were measured. Their characteristics were measured. Then their knowledge, their perception, their practice, and reducing anxiety. Like there is a particular intervention called play therapy that was used to, I mean, uh, to to reduce anxiety of patients. All right. So how, to what degree do they actually reduce the anxiety of parent and patients? That's what's the reducing anxiety measure. So then their attitude before training them about reduce the play therapy, and their attitude after teaching them about play therapy, their attitude on play therapy after they've been taught about the method. All right. So now for one sample t test, we want to perform one sample t test for knowledge, perception, and practice. So our hypothesized value is 50, and we are trying to see that is the average of knowledge, is it around, is it 50? The mean average, I mean the mean knowledge score, is it 50? The mean perceptual score, is it 50? The mean practice score, is it 50? All right, so we run everything together. You can just, anytime you need to do this, you can just edit these formulas. So we are bringing in SciPy, Matplotlib, and Seaborn. And so the population mean, that's the hypothesized mean, is 50. Now, variables for one sample t-test. Because we are testing three, if you are testing one, you can just use um, knowledge. If you are testing two, if you are testing for more, then you can use different things, because in the ideal case, we'll have different hypothesized value for knowledge, different for perception, different for practice. All right. So I just wrote all of these things together, but it can be, you can run them individually. Then store results. So we are using a loop statement to run the analysis and store it. So the Shapiro weak test is a test for normality. It checks the variable for normal distribution. Then the one then we perform the one sample t test. So to perform the one sample t test, we use the stats function. Then t tests one sample, data, population mean, then effect size, as to check the the difference between them. How does it affect, them? Then we visualize, and then we share the results. All right, so let's see. All right, so we have the distribution. All right, so this is the population mean, the 50, and the sample mean. You can see there would definitely be a significant difference here. Well, so let's see now the distribution of perception. This is for perception. It's a bit closer, and for practice, it's also closer than that of knowledge. This is for knowledge. The knowledge is really small compared to the hypothesized, the mean value. I mean the general population mean value. All right. So for knowledge, we have our p-value to be almost zero. So there is a significant difference between them. Then for the Shapiro work, this is also significant. So here we reject null hypothesis and we say the test is significant. The test is significant. All right. Then for the perception, p-value is also significantly different, because this is practically zero. That's because we have minus 14 before the 9. I mean minus 14 zeros. We have 14 zeros rather before this 9. Right. Okay, so for p-value for the third one too, there's a statistical difference between them. Right. Now for independent sample t-tests, so we want to see, does the across the gender of the nurses, were they able to reduce anxiety? All right, so this would not be a good illustration, but it's good for practice, because gender for nurses, I'm going to assume that there are more female nurses than male, right? So might not be um usually, even if they are not equal, they should be close to equal to come for effective comparison. So reducing anxiety by gender. So want to see, is there a difference in how effective male nurses have been able to reduce anxiety, and compared to how effective female nurses have been able to reduce anxiety using the play therapy. So we have the hypothesis, no difference, that there's no difference between them. That's the null hypothesis. While the alternative hypothesis is that difference exists. All right. So from SciPy, although we already done this, but we'll still run it. Now we categorize, because in our data male and female are in the same column. So here um, we put it in different, all the males in one and females in the other. All right, so we oops okay, run this. Then for the variance test, let's run the variance test. So the variance test is a test of equal variance to check if the variances are equal. So is used to check blah blah homogeneity of variance. So interpretation here, the variance statistics, it is calculated, it indicates degree of blah blah blah. So let's interpret. The p-value is 0.1. This is the key result for decision making. So if p is greater than 0.05 for the variance test, we fail to reject the hypothesis, and otherwise we reject. So here, since our p is equal to 0.1 and is greater than 0.05, we assume equal variance across groups. So now this variance test has made us realize that okay, there's no problem. The variance across the male group and the female group are equal. We can assume them to be equal. They are not significantly different. So we can continue with this test. Or even if it's not different, we just need to state it. So it's not like we've stated here, equal variance equals variance p greater than 0.05. If it is not, we say p less than 0.05. Then we have the t-stats p-value, and we'll put the male score, female score. These are the categories. Then the equal variance, blah blah. So we run this, and we have the t-statistics and the p-value. So let's go to the conclusion here. Since p is equal to 0.06, which is greater than 0.05, the result is not statistically significant at the 5% level, but it is marginally. So it is close to significant. We say it's marginally significant. So this might suggest a trend worth exploring further. That means we can suggest for the experiment to probably continue, increase the sample size, to get to see if this marginal significance will become significant eventually. All right, so it's not significant, but it is marginally. Now for the effect size, although we've learned that it's not significant, but let's see. So the effect size has a difference. How has a difference between male and female? Being a male and female, of male and female gender, how does it really affect how well you can reduce anxiety using play therapy? All right, so for CohensD, the interpretation is usually when it's 0.2 is small effects. Then we have from 0.5 is medium effects, 0.8 large effect. So this is 0.67. That's approximately 0.7. We say it has medium effects or moderate effects. All right. So being a male or female, gender has a moderate effect on how these nurses can reduce anxiety of their patients using play therapy. All right. So to visualize the effect, so you can see female have a more wider distribution than male. All right, and like I said, that could be because the male distribution is not so much. So we can check the result summary here. Then for the paired sample t-test, we have it's also known as dependent sample t-test. That's the before and after. All right, so it's used to check when if so for example we have attitude before these nurses were told about play therapy, their attitude about on it was measured. So the intervention is the knowledge on play therapy. So they were lectured about it, and after they checked their attitude again, and the measurements were collected. So for the same person, for the same nurse in this case, we are collecting two observations: before the intervention and after the intervention. This same is used in marketing and all of that. All right, so hypothesis to be tested. There is no difference between mean attitude scores before and after the intervention. All right, so this is it. Then the assumptions, blah blah. we test for normality and a lot of that. All right. So this is how paired sample t-test is conducted. So we have the before, I mean, yeah, we have the before and the after. All right. Then we drop missing values if any exist. All right. So let me run this. We have number of rows 50, number of columns 2, because we just have before and after. Now for the Shapiro-Wilk test, see whether the main difference. So what we've done here, the difference between the two of them were computed, and then the Shapiro-Wilk test was carried out to show whether it's significant or not. So since the p-test for Shapiro-Wilk is 0.3, which is greater than 0.05, data appears to be normally distributed, right? So to check the histogram and the probability distribution, you can see it's close to normality, because you can see where we have the wickedness of the histogram, and the KDE is close to a bell shape. So we can proceed with our t-test. The t-test and p-value. This is highly significant difference between attitude across before attitude scores before and after. So there is high significance between, I mean, the difference between them is very high. All right, so we reject null hypothesis, and the intervention had, we can then say the intervention had a statistically significant effect on attitude, and the negative suggests that it reduces the attitude score on the average. So probably the attitude measured is, say, their bad attitude towards it. So the knowledge gained, that's the intervention, reduced it. That's what the minus here is saying, because what we do is after minus before in the manual calculation. All right. So now for effect size, we've learned that is significant. So the effect size is -2. So this is a very large substantial decrease in attitude. So the attitude after they've been told about the play therapy was really, really reduced after. Right, so we check this, and then again to print the summarized results, this is what we have. All right, so that will be all on t-test. You can go over this again. I do not expect you to understand it at first. Go over it again, and then see you in the next video.